This video describes how we can use the nuclear-nuclear spin Overhauser effect to assign two protons that are within relative proximity within a maximum distance of about 4.5 angstroms. The application of the NOE complements information that we get from proton-proton couplings, including cozy spectra. In this class, our discussion of nuclear Overhauser effect will be limited to small molecules, but be aware that NOE data is critically important in the characterization of biomacromolecules by NMR spectroscopy. This example from Chapter 3 shows how we can use NOE difference spectroscopy to assign all of the proton resonances in this dimethyl substituted pyrrone. The top spectrum is the proton NMR. The second spectrum arises from selectively irradiating the peak at 1.9 parts per million, which leads to an enhancement of only one of the other protons in the spectrum. The complementary experiment then involves irradiation of the other methyl group at about 1.3 parts per million, and this leads to NOE enhancement of both of the alkene protons. From the combination of these two experiments, we can assign the methyl group at 1.3 parts per million to the methyl group on the carbon between two hydrogens, and the other methyl group is then bonded on a carbon adjacent to only one alkene hydrogen. The spectra that are presented in Chapter 5 are the two-dimensional NOE experiments, which are commonly known as NOESY correlation experiments. Technically, the application of two-dimensional NOE experiments with small molecules, as studied in this class, is best accomplished by a variation of the NOE experiment known as the rotating frame Overhauser enhancement experiment, or ROESY. This slide shows the proton NMR spectrum of a terpene known as pinene diol. The NMR spectrum has already been assigned for all of the protons within the cyclohexane in the back, but without assigning any of the methyl groups. On your own, I encourage you to practice determining coupling constants by deconvoluting the various multiplets that are shown in the expansion. Moving to the carbon-13 NMR spectrum, this spectrum shows 10 chemically non-equivalent carbon resonances. We can then correlate between the proton and the carbon spectra with HMQC. We can assign some of the resonances on this structure based on the chemical shifts. So carbons A and B at about 70 parts per million correspond to carbons attached to the electronegative oxygen substituents, with A attached to no protons and B attached to a deshielded proton lowercase b. This spectrum has already labeled all of the protons corresponding to the carbon atom to which they are attached. So this is different from the labeling that I typically use. By process of elimination, the other quaternary carbon, E, must be this carbon, which is a bridging carbon substituted with two methyl groups. The HMBC spectrum gives a lot of information, and I will touch on only a few items which help to clarify some positions. But what this tells us is that for carbon B, showing a correlation to a proton attached to carbon F, that allows us to assign F as the methylene that is bonded to B. This is then confirmed by a 3-bond correlation from carbon A to proton F, at least to one of the protons at F. This also tells us that carbon B has a 3-bond correlation with a methyl group, protons G, based on this correlation. The assignment of the other methylene, H, is primarily by process of elimination, but we see some correlations between the carbons and the protons of H and F, as well as a correlation of carbon E with one of the protons of H. The COSY spectrum prominently shows correlations with each proton of F with proton B, corresponds to this portion of the molecule, as well as the 2-bond couplings between the protons on F and the protons on H. One thing that also stands out is that the protons at H correlate with protons D and C, and that protons C and D are correlated. So what that tells us is that there may be a connection between C and D involving 4-bond coupling. From the chemical shift, we might tentatively hypothesize that carbon C and the corresponding proton are closer to the hydroxyl group than carbon D and its proton D, but that's merely a hypothesis. The NOESY spectrum provides information in addition to what we already know from COSY. So new correlations along proton B include a correlation of proton B with the hydroxyl, so that's consistent with this assignment, as well as new correlations through space for proton B with proton G on the methyl group, and proton J, which is another methyl group. That allows us to make an assignment of the methyl group nearest proton B as J. A new correlation in the NOESY between F and J also confirms this connection, and in fact it points out which proton F is up, which allows us now to call the other proton F as F prime. Another NOE correlation between protons H and I tells us that the remaining methyl group is near the proton that is up on carbon H. That allows us to assign H prime. Correlations of I with C and D don't add any information. However, the correlation of proton C with proton G now helps us confirm that carbon C is attached to carbon A. And by process of elimination, we can now assign carbon D and proton D. The second example for NOE type experiments is depicted in the textbook for a tetrapeptide. Although it is not stated here, the polar peptide is undoubtedly dissolved only in polar solvents such as D2O. That will result in deuterium exchange of the hydroxyl proton and also the ammonium proton, and under neutral conditions, deprotonation of the carboxylates. The analysis begins by focusing first on the deshielded region, which corresponds to the amide NH groups. The portion of the spectrum around 4 parts per million then corresponds to hydrogens on carbons that are bonded to the heteroatoms nitrogen and oxygen. And then the remaining protons are for the side chains, for protons on carbons that are not directly bonded to heteroatoms. None of the specific assignments that are provided here can be made solely on this proton spectrum. This is where correlation spectroscopy is invaluable. At the outset, it's difficult to make any assignments. Perhaps this broad triplet could correspond to glycine with 2 hydrogens on the adjacent carbon. But what we can only say with confidence is that the cross peak fits with this apparent doublet of quartets at 4 parts per million. Likewise, for the next NH, we can see a cross peak with a single proton at the alpha position. Only later can we determine that it is this correlation specifically for serine. Likewise, for the third amide NH, we can see a correlation with a CH that is attached to nitrogen at the alpha position at 4.2 parts per million, and ultimately that is later determined to be specifically for glutamate. The total correlation spectrum helps us to link specifically each NH to the rest of the side chain. So for glycine, which does not have a side chain, this correlation is simple. For serine, the NH we've already established by COSY was linked to a peak at 4.5 parts per million, which is further linked to a 2H multiplet that is attached to a heteroatom at 3.8 parts per million. This happens to overlay with another 1H group, but ultimately it can be determined that there is this correlation for an amino acid that fits the structure of serine. And then for the third amino acid, this NH, which is connected to a C2 hydrogen also correlates with clearly diastereotopic methylene, and then another methylene group with the protons much closer together in chemical shift. And that fits a pattern for glutamate. However, from the toxi spectrum, we don't have a sequence of the amino acids in terms of how they are linked together. We're also not seeing a correlation with valine, but that is because the nitrogen of the ammonium group is fully deuterated. It is the ROESY spectrum, building on knowledge from the COSY and the toxi spectra, that allow us to connect the specific amino acids together as peptides. For the glycine in H, there is now a new correlation with the hydrogen for valine. It does happen to overlap with serine hydrogens, but upon magnification, this can be detected in the primary spectrum. And there's also a through space correlation with the 3 hydrogen of valine. Continuing with serine, we can see that the NH of serine now has a new correlation with the CH2 of glycine. And then for glutamate, this NH is showing a correlation with the serine hydrogens, and this also correlates with an additional pair of hydrogens on serine. This is how the tetrapeptide is constructed from the individual amino acid components. Upon looking at the full COSY spectrum for the remainder of the compound, which is not shown here, correlations with the methyl groups of valine can also be established.